this video, we'll look at the last part of example 2, and this example was on the sampling distribution of the sample mean of call center wait times. These wait times were normally distributed with a mean of 10.4 minutes and a standard deviation of 3.2 minutes. The last part of this is part F. Part F says that suppose that 30 customers are randomly selected. There's a 25% chance that the mean wait time of these 30 customers will be at or above how many minutes? So what they're getting at here is they're giving us a percentage, and remember that percentage is another way of expressing probability. So that 25% is in a way like a probability. And what we're trying to find is the mean wait time that's the cutoff for that 25%. So again, this is involving a sample of 30 customers. It also mentions mean wait time, and both of those are clues that we're dealing with the sampling distribution of the sample mean. So before going any further, you want to make sure to calculate the mean of that sample mean. It's still 10.4, and the standard deviation of that sample mean by using this formula, and it comes out to 0.584. So this is just the population standard deviation divided by the square root of the sample size. And again, in this problem, what they're asking for is a particular mean wait time. We don't know what it is, but let's just call it x bar t. And it's going to represent the cutoff for the top 25% of wait time sample means. So in the problem, they use the phrase at or above, and that indicates that this is a cutoff wait time, and it's at the higher end of the normal curve. So in other words, it's some wait time that's near the right tail of that curve. If this had said at or below, we'd be talking about the left side of the curve. We'll draw an illustration to show what this is saying. Here's the curve, the mean is 10.4. And what it's saying is that there's some sample mean, which we don't know what it is exactly, x bar t, that's the cutoff for the top 25% of sample means. So in other words, the area above, or the area to the right of xt, is 0.25. So 25% of sample means would be above it, and 75% would be below it. This area right here is, remember, the area is the same as probability. So it has, this just means this is the probability that a sample mean is greater than x bar t, and that probability is 0.25. There are different ways that we could solve for x bar t, and one way is to use a graphing calculator. And for this problem, because we're trying to calculate the value of x, or x bar, and we know the probability, you'll use either inverse norm on the Casio or inverse norm on the TI. Also, just keep in mind, just like in Chapter 7, when you do these kinds of problems, the calculator will ask for the area, and usually the calculator is referring to the area under the curve to the left of x, or x bar. So if we were doing this problem from scratch, it helps to draw out the curve. So this is the information that we have. And again, remember that the calculator, it is actually usually needs the area that's to the left. So we know this is 0.25, but the area to the left would be the complement of this. So this area is going to be 1 minus 0.25, or 0.75. So we get that complement, 0.75. Now that you have the area to the left, when you use the Casio calculator, you would take these steps, get to the function called inverse norm. The tail we'll use is the left, and the area to the left is 0.75, just like what we found up here. Put in the standard deviation and the mean on the TI calculator, take these steps, get to the function inverse norm, and you put in the area to the left, the mean, and the standard deviation. And either way, you should end up with this result for your sample mean, 10.794 minutes. The other way that you could do this is by using a table. And so the first step, as always, is to draw out that normal curve. When you use the table is also based on the area to the left. So you would have to still consider the same thing, and the area to the left is going to be the complement of the area to the right. So 1 minus 0.25, and really we're going to be using 0.75 for the area. Then we'll go to the table, and we'll look in the middle for the value that's closest to 0.75. And it's kind of a toss-up. This is 0.7486. This one's 0.7517. You could probably use either one. This one is a little closer to 0.75, so maybe I'll use this one. And the z-score that is for that area is 0.67. So we'll use a z of 0.67. Now that you have the z-score, you can use the z-score formula and plug in the mean, the standard deviation, and the z. So we'll plug all of those in. And the thing that we are looking for is that x bar t. We're still looking for that sample mean. Solve for that x bar t. So multiply by the standard deviation on both sides, then add 10.4 on both sides. And when you solve for it, you end up getting 10.791 minutes. Pretty close to that result using the calculator. That's the last part of that example. There are a couple takeaways that you want to keep in mind from this section talking about the sampling distribution of the sample mean. One takeaway is that keep in mind if the population is normal or if the sample sizes are greater than 30. So if either one of those is true, then the distribution of the sample mean is also normal. Another takeaway is that if this sampling distribution is normal, you'll use the same methods as we did in Chapter 7. So I've mentioned that before, and you probably have noticed that we've really been using all of the same methods. And the last takeaway is that we're using all of these same methods. The only difference really from Chapter 7 is this extra step where you may have to calculate a new standard deviation of the sample mean by using this formula. Other than that extra step, all of the other steps are almost the same as what you do in Chapter 7 with a normal distribution.